Okay, so what we're going to look at today is we're going to look at a special type of event, one which we call mutually exclusive. And just to give you an idea of the process, we're going to compare a couple examples. So to get started, let's just say that first of all, we're going to guess a number between 1 and 15, and the number could be even or odd. So in a Venn diagram, we could try to represent this. For example, if I make A the even numbers, then I would put 2, 4, 6, 8, 10, 12, and 14 in that part. And when the B represents the odd numbers, I'd have 1, 3, 5, 7, 9, 11, 13, and 15. And from the Venn diagram, we can then talk about some probabilities. So what's the probability that A occurs? Meaning, what's the probability you guess an even number?
7.
Yeah, there's 7 items in A, so it would be 7 out of 15. What about B? Yeah, so there's 8 out of 15. How about the probability of A and B?
0.
Yeah. So this basically says this is impossible. What about A or B?
1.
Yeah, all items are in there, so 15 of the 15. So you're guaranteed, this is certainty, that you're going to be A or B. So sometimes you lose track of the math when you just get a bunch of numbers in front of you. But what we've got here are even and odd numbers. So for the integers from 1 to 15, it's got to be either an odd number or an even number, meaning all the numbers are one of those two. That's why it's certain you'll be even or odd. It's impossible that you be both. There's no number in 1 to 15 that is both even and odd. I don't know that there is a number that's both even and odd. So I'd like to see it if you can come up with one. But okay, now we're going to take a look at a different, slightly different example. This time, from 1 to 15, A represents even numbers again, but B represents multiples of 3. So when we just did counting in last unit, the first thing we always tried to count was the thing with the most conditions, the thing which was going to be most difficult. So a Venn diagram, that's a good strategy for your Venn diagram as well. You should start by choosing the most difficult condition, which is going to be those numbers which are both even and multiples of 3. So those numbers would be 6 and 12. They're even multiples of 3. Okay, it just makes it easier for me now when I pick the rest of the numbers. So the even numbers, those are the numbers 2, 4, 6 is already in there, 8, 10, 12 is already in there, and 14. The multiples of 3 I haven't included yet are 3, 9, and 15. And what's missing? Well, the odd numbers that aren't multiples of 3. So that would be numbers like 1, 5, 7, looks like 11, and 13. Okay, so let's say what's the probability? Well, we know this one. We already answered this in the first question. So that's 7 out of 15. What's the probability that you are a multiple of 3?
1.
Right. So 5 out of 15 or 1 out of 3. Okay, what's the probability that you are even or a multiple of 3?
2, 3.
Yeah, 10 items out of the possible 15, so that's also 2/3. What's the probability that you are both even and a multiple of 3?
2 over 50.
Good, yeah, there's 2 in that part of the Venn diagram. So we talked about this last day just briefly. We mentioned how you can come up with the formula for probability of A or B, probability of A and B, and we just want to show you here the 2 different instances. The formula works for both. Does anybody remember how we came up with it? How do you come up with A or B? Nope, everybody was absent last day, I guess. Okay, no problem. So what we're going to look at today is where the formula comes from for calculating A or B and A and B. So let's take a look at the Venn diagram and we'll come back. So here's the Venn diagram, and what I'm going to do is I'm going to shade in the event A. I'm going to shade it in as red, and I'm going to shade in the event B as green. So what you can see is in the overlap, how many times has the overlap been counted? Yeah, the overlap is both red and green, so it's been counted twice. What will we call the overlap? Intersection, but probability of what? That's A and B, where they overlap. So that means for my event here, if I was to take A and add B, then I would double count the middle, because the middle has been counted once in A and then again in B. So what I have to do is I have to remove that duplicate. So I'm going to subtract the probability of A and B so that I don't double count it. Now, if we just take a look at the example we did above, just to verify this, we did the whole sample space, we looked at all the events, but in this one, for example, if I take A, B, and I subtract A and B, I have 7, 5 is 12, minus 2 brings me back to 10, exactly what I was hoping for. And it still works in this situation over here. 7 and 8 is 15, minus nothing is still 15. Okay. So let's take a look here. Mutually exclusive, basically the technical way to think of mutually exclusive is that means there's no overlap. So the probability of A and B equals to 0. And the way you want to think of that is this is when two events cannot happen at the same time. Okay, so we'll talk about some of those examples and what they might look like. But here's the Venn diagram for mutually exclusive events. Okay, this is for normal. I guess we shouldn't really call it normal. Let's call it non-mutually exclusive. And this is the mutually exclusive picture. So since there's no overlap, probability of A and B equals 0. So one nice thing about mutually exclusive events, if they can't happen at the same time, that means there's no overlap. So this part of our formula is a 0. So for mutually exclusive events only, for mutually exclusive events, it simplifies the formula to just the probability of A or B is just A plus B. If A and B are mutually exclusive. Sorry, I'll let you copy that down.